Alright, so sounds a bit theoretical, I know, so let's go a little bit deeper on what it actually means. Yeah? So again, we have an arbitrary, in this case a discrete signal x. Yeah? So this is x of n and this is n. We feed it into an LTI system, and basically our goal is to know what the output is of that system through the LTI system. Yeah. So basically, what we're gonna do is we're gonna decompose that complex signal in a set of delayed impulses. Yeah. So this delta here, we call this the impulse, the unit impulse. Unit impulse. It's basically the Dirac delta function, but you can forget about that. So, and decompose means that we decompose it in this piece, then this piece, but this is delayed with 1. And then the longest piece here is also delayed, but by 2. So, and basically what we want to do is, if we add all these delayed impulses up, and we multiply them first with their weight. By the way, these x's here, they are the weights. Yeah? So we have x0, which is basically the height of the pulse, times the unit impulse. Then we have plus x of 1, which is the height of this one, right? Times the Dirac delta of n minus 1 plus x of 2, which is the height of this one, and then the Dirac of n minus 2. This is how we actually now decompose that function. And we can write this simple around with the sum of x of k and then delta n minus k. And k goes from minus infinity to plus infinity. Yeah, this is just the short version of this one. So, how do we now calculate this y? We're still not there. So this is step 1, we decompose. What we're now going to do is we're going to determine what the impulse response is going to be. Yeah? So now we're going to look at the unit impulse response. Here we are. So assume that the impulse response, which we call h of n here, h of n. Assume that this is the impulse response for this situation. Here the response is going to be exactly the same but delayed with the unit. So we move 1 to the right. Here again, but here we move another 1 to the right. And so here we now have calculated our unit impulse responses. So now what we're going to do is we're going to use these two to calculate the response of the system. Yeah. All right. So there's we're almost there. Yeah. So basically, what we've done is we have decomposed x of n in a linear combination of unit step functions, or I would say linear combination of delayed unit step functions, yeah, which are these deltas, unit impulse or step functions, yeah. So by the linearity the linearity feature of LTI systems, we know that a linear combination of delayed unit step functions at the output will be a linear combination of the responses to these unit step functions. That was linearity. Remember, we had two systems. Yeah, this system 1, this system 2, and here we had a third system. Remember, here was alpha x1 plus beta x2 resulted in alpha y1 plus beta y1. Yeah, this was the linearity feature. So that means that a linear combination here of delayed unit step functions, yeah, results in a linear combination alpha beta in the responses. So x1, x2 now goes to y1, y2. But we know the response of that unit step function. Yeah, so this is now so y of n is now a linear combination of x of k, and then the response to that unit step function is hk of n. Yeah? So this is the response to these unit impulse functions, right? So that is by linearity. And now we're going to use the second characteristic. So by time invariance, so now we're going to use time invariant. Yeah. What does time invariant mean? It means that the response to a unit step function at time k, yeah, is the same as the response to that unit step function at time 0, but shifted over k. Yeah, is exactly the same. So now we're gonna drop this 0, we're gonna drop it. Yeah. So basically, what we get in the end is that the output of my LTI system equals the sum k equals minus infinity to plus infinity, yeah, of xk. Yeah, we have not moved or not touched the signal, and then we replace that by that h n minus k. Yeah, it's not so difficult, right? We have a signal, we decompose into simple basic unit impulse functions. Then we're going to look for the response to these unit impulse functions. Yeah. So the responses are the h's. Yeah. So because the input is now written as a linear combination of the unit step functions, the output will be a linear combination of the responses of these step functions, which are the hns. And then we use time invariance, that your response at time k is the same as your response at time 0 shifted over k. This is the time invariant feature. Now this here we can write as the output of the system equals, yeah, x convolve with h, right? And that is basically what convolution is, right? So let me repeat. And this operator here is actually this one. Now this is our operator to show convolution. So from signal theory is that in order to find the output of a linear time invariant system, we just convolve the input of that system to the unit step responses. Yeah? So we convolve the inputs with the unit impulse responses of that system. And that will give us the output. Yeah? No matter how complex X of n is. Alright, so now that we've seen where convolution comes from, I'm planning to give you a bit more intuition based on a more specific example. But first we will need to go from one-dimensional to two-dimensional. Yeah? And this will not take a lot of time because we will use the analogy.